All right. So I think it's recording. Oops, şöyle bastım. I think you can see my screen again. So we generated this mesh of 16,000 elements, and then that's it. I think this mesh will work for us. And we will go to this study. We have options under it. And then we have this compute button. I will not change anything like default settings. And then I will just say compute. Now, here is the result. It's quick. Two-dimensional simulations on today's computers can be done in a couple of seconds, actually. When it is a three-dimensional simulation, it will be like a couple of minutes, maybe a couple of tens of minutes. And it's a complicated one, maybe it will be a couple of hours, but this is done in like 7 seconds. So in 7 seconds, we just calculated this solution. And we have a convergence plot here. So we have some errors versus iteration numbers. So solution is done a couple of times to reduce the errors. So in like 6 iterations or so, we reduce the error to a certain default tolerance value and we're happy with it and so on and so forth. The details are not that important. So where is my so all right. So what is this thing we are looking at? It generated a default, like a contour plot, and here under the results, so let me again minimize these so it doesn't look crowded. Oops. So we have this results, and then under it, so console generated for us a velocity and a pressure. So if I just click on those, the one we looked at originally, this one, this is the velocity plot. So this is the velocity magnitude, so it's the speed. So it's lowercase u square plus lowercase v square, and then square root of it. So it's the speed. So speed is calculated inside every cell, every element. And since we have lots and lots of elements, when we plot it, it looks like a smooth, nice variation. We can zoom in, we can zoom out. And then as you see, we have like a legend here, a color bar. 0 is the minimum speed. It's the no slip condition on the walls. So the walls are just 0 and the fluid close to the wall is like low speed. And the highest speed is, I don't know, 1.2 10 to the minus 2. 1.2 10 to the minus 2. That's kind of the highest speed. And that occurs like at the center line, at the exit or something like that, right? And we have a flow development part, and maybe it became fully developed somewhere here. I don't know. We can check it, and then the rest is like fully developed. And then we have the pressure contours also generated for us. So for the pressure contours, we just see some lines because it says here under contour, I think the line option is selected. Yes, we can just change it to field, and then it will be a field pressure contour. So this is the pressure contour, and pressure contour is kind of very simple. There is, so in the initial fully developing part, the entrance part, there is a nonlinear pressure drop. That's what we expect due to entrance effects. And then after a certain point, if fully developed is reached, after that, there is a linear pressure drop, right? And then actually it is the case. I mean, we cannot see it easily from these colors. We can plot like the variation of pressure at the center line or something like that to see it better. But again, this one also tells us a little bit of that pressure story. And we have like localized high pressures close to the corners. Remember, we have uniform, constant speed flow coming in, and then very suddenly that flow meets the no-slip top and bottom walls, and then it just goes through like very strong deceleration, right? And that creates a lot of high pressure gradients close to this corner and also close to the bottom corner. So these two corners, we have like pressure forces rather high and then decelerations rather high. So the fluid just rushes in towards the center line, and then we have a flow like that. We can just visualize different things here. I can just go to, I can say maybe velocity, and then I can say an arrow surface. And I can disable the surface. Oh my God, this is working very slow today. I don't know why. I wanted to disable this. It is disabled. So let's plot this. Oh, why? I'm sorry. I want to disable this one so that only the other one is visible. Oh, come on. All right, I will just get rid of it then. Delete. All right, so this is another type of visualization. And here we are seeing some velocity vectors, right? I can maybe increase the size of these arrows, all right? And then to make sure that we have like fully developed flow or not. So what is going on? If you zoom into the entrance, we have almost uniform flow, but some deceleration close to the walls due to the no-slip condition. And that deceleration propagates into the domain, and then the flow field becomes, the velocity profile becomes like a parabolic profile almost, not perfectly, but it is trying to become a parabolic-like profile, right? And then, for example, if you look at this profile and then this one, they're pretty much the same. And this one, not that different. So we have kind of a flow that is trying to become fully developed. Maybe not exactly fully developed yet, but something like that, right? So what else? So we can plot streamlines. We can go to results and then say a 2D plot group. And then under the 2D plot group, we can select a streamline. And then we can just say release streamlines from this inlet, which is meaningful, and then plot some streamlines. So another kind of visualization that we can do. So it is almost straight everywhere, but not exactly. If you again zoom in towards these corners, there is a kind of a little bit of rushing in, right? And then we have pretty much very simple, straight streamlines parallel to each other, laminar, nice flow, right? So streamlines are not that interesting. They are kind of quite simple. I can generate a center line here. I can generate a center line going just exactly in between the two plates, and then I can plot the variation of pressure on that center line, for example, to see the pressure variation better. But this solution that I'm looking at is not exactly the same as the one I have in my notes. I don't know why. Maybe I just input some of the settings different than I did before. I want to check here the boundary conditions. For the outlet, we said zero pressure. For the inlet, we said 4.01 meters per second. And then that looks okay. For the fluid properties, we have 1010 to the minus 3. That also looks okay. I don't know why it is different than the one I did before this morning, but it looks a bit different, so I don't know why. Probably I entered something different when I was solving it earlier. All right, I was saying that let's generate a 1D, where is it? Cut line 2D. So we will just generate a cut line going from this center at the inlet to this center at the outlet. So it will go from 0 to 1. So these are the endpoints, XY coordinates of the 2 points that defines the line. Then the Y's are just 0.05, this Y value here. And then this is again 0.05. So if I just plot it, it is, this red center line, right? So it's cut line 2D1. We can change these names. For example, we can say, rename it and make it like center line, so that it becomes a meaningful thing, center line. So I generated a center line. And then I will just come here, results, right click, 1D plot group. And then I will say on that 1D plot group, generate a line graph. And I will generate a line graph. So the x-axis of that line. So here I will just go with the center line that I created. So on that center line, I want to plot something. So on that center line, I will plot on the x-axis. It will be like, it can be arc length, or it can be like an expression. I can say an expression and then say this, the x coordinate. So the x-axis is the x coordinate, right? And then the y-axis is just pressure. So I will just say pressure, right? So y-axis data is pressure, x-axis data is x, and I just plot it, and I will see, a pressure variation like this. So is this expected? Is this meaningful? So this is how the pressure varies at the center line of my two-dimensional channel, right? So initially in the entrance part, there is a nonlinear pressure drop. And then after a certain point, maybe roughly this, it becomes kind of almost constant, right? So this is the fully developed part, roughly. And then this is the flow development part. In the flow development part, we have kind of excessive pressure drop. So if you extend this linear part all the way to this entrance, this is the entrance. So there is a little bit of extra pressure drop here, and that is due to the entrance effects, the accelerations, decelerations, the flow development effects, right? So this is exactly the same picture we have in Munson's book. So if I go to Munson's book and then find the viscous flow in pipes, and then here is the figure that I'm trying to see, this one here. So this is for a pipe flow, but it is not that different for a channel flow also. We have a constant pressure drop region, fully developed region, dpdx is constant. And then we have somewhat an excess entrance pressure drop. And pretty much this is what we have in our simulation also. So this plot is kind of similar to the one we have in our textbook, right? We can calculate this pressure drop, the constant pressure drop in the linear part. For example, I can pick a pressure value here, I can pick a pressure value here, and then subtract those two pressure values and then divide by this distance. And then that will be my dpdx. And then I can check whether that dpdx and the other variables that I entered, like viscosity, density, average speed, and all those things, they match with the analytical solution with the theory or not. And most probably they do match, right? So I can just plot also U here. I will change this pressure to U. So I will plot the x velocity component on the same streamline. So when I say plot, so this is what I get. Oh, this is kind of a bit not expected, right? So why is it like that? I'm a bit puzzled. So we start with 0.01 at the entrance. This is the specified boundary condition. And then it increases. And then it tries to become like parabolic. But it is not parabolic at all. I'm sorry, I mean, we cannot see the parabolicity here, but it tries to become constant. It tries to stabilize, because that's what fully developed means. Velocities are no longer changing in the flow direction, but it is not like that. Oops, I clicked on something. What did I do? I screen share'imi kapattım. I'm sorry. I think I just, what did I do? Share. All right. Nice. I did something. I don't know why. Oops. Why do we see? So let me put myself here so that you can see me. Right. Oops. Small. Sorry. Alright. So normalde beklediğimiz ne? Constant verdiğimiz inlet speed artacak. Fully developed region'a eğer eriştiysek ondan sonra artık artmamaya başlayacak. Sabit kalacak. Bu sürekli artmaya devam ediyor. Bu yine benim bu sabah yaptığım çözümle tam olarak uyumlu değil. Bir şeyleri ben farklı yapıyorum ama ne yaptığımı anlamadım. So one thing we can try is so let me go to the book again and then, oops, not this one, to the book, and then let's go to the earlier simple solutions, Navier-Stokes solutions part. And then in the fully developed part, here we have Umax is equal to 3/2 times the average speed. So it is 1.5 times the average speed, the Umax, the center line speed. So our inlet speed is the average speed. It's 0.01. We specified it as 0.01. So 1.5 times of that, 0.015. So the center line speed should stabilize at 0.015. But it is, so it is 0.015 daha gelmemiş. 0.015'e daha varmamışız. So we have, maybe we have to provide a longer channel to see that 0.05. I will do that. I will try that. So I will just go to geometry and I will double the length of my channel, right? So for geometry, I have this rectangle and it had originally a width of 1. I will just say maybe 2 and then we'll select it, right? So it is now a longer channel, 2 times longer, right? I will not select anything else. Maybe I will just generate my mesh again. It will be just, again, a simple mesh of square cells. And I will go to study. Since it's a quick solution, I will just compute it again to check whether fully developed part can be reached now or not. Right, so it is solving. It will take a little bit more time, but in 12 seconds, again, it's done, finished. So this is our solution. So let's again go to line graph 1, the same graph, and then plot it again. Oh, but my center line is now not long enough. I define my center line from 0 to 1. It should be from 0 to 2, all the way to the end, right? So yeah, from all the way to the end. So now I can go here and then say, show me my plot. Oh, it is still increasing. Still, it's not 0.015. So I'm trying to see 0.015 here, right? And it is kind of not fully developed yet. So I need a longer channel. All right. I think I will just make it longer because I really want to see that fully developed region and I want to check whether 0.015 can be calculated or not. So I will just make it, I don't know, maybe 5. I don't know. You'll select it. So this is now a really long and thin channel. And I will just create the mesh again, right? It will be now a mesh of 80,000 cells. It's a bit too much for a simple two-dimensional flow. Maybe it's too fine, unnecessarily fine. I will go and just compute it again. Maybe it will take like half a minute or so at this point. See whether this is enough, long enough to obtain fully developed conditions or not. We will see. So we have a progress bar here. We're trying to reach a convergence. This is error versus iteration convergence plot. And then, yeah, it's done in like 23 seconds, very fast solution. And then again, I will just change this center line length to 5. So it is a line of length 5. And then come here and see what this graph is doing now. Oh, yeah, almost there. So we are almost there. So once again, this is velocity, x component speed versus the x coordinate. So it's the speed variation, u variation on the center line. It starts from the inlet condition and then speeds up and speeds up and speeds up, and then it just kind of not changing anymore. And we are almost at 0.015. If I make the channel slightly longer, a bit longer, I think fully developed condition can be seen. And if I just change this to pressure again to see the pressure variation, plot it again, yeah, this is the pressure variation. So this part close to the end is almost straight line. And if I extend that straight line all the way to the entrance, there is a bit of extra pressure drop here. So that's due to the flow development effects. Bu kamera neden beni göstermiyor da başka yerleri gösteriyor acaba? Maybe I just don't know how to use it. Right? So if you have any questions, you can ask anytime you want. You can also write it to chat if you want. And so that's it. Again, like I said, we can just pick 2 points here on this line. So I can just pick 2 points and their pressure values and how much apart they are from each other, the distance between them. Just divide the pressure difference to the location difference, the length, and then we will just do a little pressure gradient calculation there and see that whether that pressure drop matches with the theory or not. All right, so let's do some more plotting. I will just go here and then I will generate another, oh, not here, but I will, yeah, I will. All right, what I can do is, yeah, I want to see that parabolic pressure velocity profile at the end. So I will generate another 1D plot group, and there I will generate another line graph. And for that line graph, at the exit, here at the exit, I will plot that parabolic velocity profile. See whether it's really parabolic or whatever. And then there I will just say, just plot it at the entrance, at the exit. So 4 is my exit. So I selected exit. So it will be plotted on that line. And then y-axis is just y. And then the x-axis is an expression. Oh, sorry, yanlış bastım. Oh, come on. It's an expression. And then it will be, yeah, u. I can just say u or spf.u. So those are like the syntax of COMSOL. So I can plot many, many different things. So if I just come here, I have lots of things that I can plot. For example, under laminar flow, under auxiliary variables, I can plot total viscous dissipation, mass flow rate, average pressure, volume flow rate, viscous stress, total fraction, this and that. Many, many, many things are available and I can plot. I'm here playing with basic variables. So U is just U, V is just V, P is just P, but we have many, many more advanced complicated expressions that we can use here. So I will just plot it. And yeah, this is the parabolic velocity profile. So this is the y-axis, and this is the U variation. And then no slip condition at the bottom wall, no slip condition at the top wall. And then we have kind of a parabolic profile. I can also plot the exact solution on top of this, but I need to enter it like a couple of numbers on the exact profile and see whether they match or not. And then this maximum one should be 0.015, and it is almost 0.015. As you can see here, it is 0.0147. So if you round it, it is like 0.015, right? It is 0.015. So this seems to be correct, right? This seems to be correct. You may say, oh, this is very simple. I mean, we should use CFD for more complicated things. Yeah, correct. It is simple. But remember, we don't have an analytical solution even for this problem. We have the analytical solution only for the fully developed part. But we solve both the entrance region and the fully developed part. So for this one, we don't have an analytical solution, or maybe in a more advanced textbook, more advanced than ours, there may be, but it will be kind of a long, hard to obtain analytical solution, maybe in the form of infinite series or something like that, right? So it's not easy even to solve this one analytically. But with CFD in like half an hour, we can just obtain a solution. And then this is the starting point, right? And then we can make it more and more like interesting and fun, right? So maybe şöyle bir şey de yapabiliriz. So let me create couple of other uh, uh, 2D cut lines, and then I will just say, let's say close to the entrance, not at the entrance, but right after the entrance, I will create another vertical cut line and I will plot the velocity profile there also. So it will be like 0.01, or what was the height of the channel? It was 0.1. So let's make it 0. Maybe 1, and then y is 0. Here y will be 0.1, and then it will be 0.1. So we have 2 points, 0.1 and 0, after the entrance at the bottom wall, a point, and then after the entrance, another point at the top wall. So if I plot it, I just created this line, right? I just created this line. And then I will say additional parallel lines with distance of 0.1. And then what will this do? Plot? No, in the other direction. Minus. But yeah, I generated 2 lines, and then maybe comma minus 0.2, comma minus 0.3. I think it will generate more lines. Yeah, I generated a couple of lines close to the entrance. And then I will also plot the variation of velocity on those lines to see the flow development effects. And maybe I can just do a couple of more, minus 0.4 and then minus 0.5. And we will see whether they are enough or not. So I generated how many lines? 1, 2, 3, 4, 5, 6, 7 or so lines. And they are called cut line 2D, 2. I can just rename it again because it's a stupid name. So like entrance lines or something. This is equally stupid, but it is my stupid naming. So I can maybe remember it. So I will come here and then I will say under this one, another line graph. And on that second line graph, I will just select my entrance lines and then plot plot the same thing. I will just plot u, y, and then I will say plot. Oh, yeah, this is a beautiful graph now, right? So this blue one is the exit plot. So this blue one is the one at the exit velocity profile. And then this green one is the one closest to the entrance, but not at the entrance, just right after the entrance. So it is not a perfect straight line. We have no slip condition, accelerations, and such things. The red one is just the one after that, and then this whatever color one is the one after that, and then the pink one. Oh, your meeting will end in 10 minutes. Okay. And then the pink one, and this yellow one, and then the black one, and then so on. So if I put a few more, actually it may be a more complete and beautiful picture. Just for the sake of fun, I will do that. I will just come here for the entrance lines. I will put a couple of more distances, minus 0.6, minus 0.7, minus 0.8, minus 0.9. Oops, this is not correct, I guess. We have to use the correct syntax. So let's see whether it is correct or not. Yeah, I generated a couple of more, I guess. And then I will just come here and then see the new result. Yep. Not yet there yet. So there it's not fully developed, but I need to put a couple of more. But you can see the developing flow here nicely from a uniform entrance due to the no slip condition at both walls, we just have a developing flow, right? And the flow is developing and the velocity profile is changing. It's becoming more and more parabolic, closer and closer to this parabolic. And then eventually it becomes parabolic, right? Tabii bunları equally spaced vermemize gerek yok. Mesela 0 nokta bundan sonra -1 diyelim. Sonra -1,5 diyelim. Sonra da -2 diyelim. Right? So they don't need to be equally spaced. So what are those? So ne oldu ya? -0,7, -0,8, -0,9, -1, -1,5. Eksileri unutmuşuz. For some reason I need to put minuses there. I don't know why. So here it says the positive direction is this direction. So I put a line here and a line there. So I didn't want to put lots of like lines close to each other, but I just wanted to separate them. So I just added this yellow one and then this black one. So still not fully developed, but it is just almost fully developed, right? Almost fully developed. All right, so maybe we can also end this second part and then I will again just start a new session, right? And there we can just maybe put maybe we can put an object in this channel, like an obstacle, like a circular obstacle or a square obstacle or something like that, and see how flow goes over that obstacle so that it becomes a more interesting flow field. And then maybe we can just do a couple of other things inside this channel. So I will stop the share and I will stop the recording also. And then I will start a new session and then you can come in and join.